On a family trip to India, I saw the glaring water gap. There was a lack of access to clean water, and despite the precautions my family and I took, I still fell ill from drinking contaminated water. When I returned home, I found that this was a global issue. 2.1 billion people across the world lack access to clean water, and an estimated 1 out of 3 drinks from such severely contaminated water that they are at severe risk for waterborne disease. And the current solutions are simply inapplicable, inaccessible, and often very costly. This meant that there is a clear need for a cost-effective and globally applicable microbial contamination detection system. NARID is a cohesive device with an imaging system, AI processing, and a transmission system that utilizes neural networks to detect any microbial contamination that may be present. Beginning with the imaging system. As I did not have access to a traditional laboratory environment and there were no pre-made microbial data sets, I had to create my own. I utilized non-toxic microbes such as Streptococcus thermophilus, Saccharomyces cerevisiae, and Lactobacillus. I created various combinations and solutions of these microbes, took 3,000 images, and divided them in a 2-to-1 ratio for training and testing. I then moved on to the creation of my microscopic camera. As I wanted this to be affordable, I decided to use a Raspberry Pi camera, an optical tube, a 10 magnification optical lens, and a 40 magnification objective lens, which made the final magnification 400. This would create my cost-effective microscopic camera that would constantly take images of the water sample and transmit it to the AI processing for analysis. Moving on to the AI processing, I created an 11-layer neural network with 2 features extracted, shape and size, because microbes vary greatly depending on these 2 features. In my neural network, I had multiple types of layers such as convolution, which is where features are extracted, and max pooling, which is where downsampling occurs. I also had to pick an algorithm which would determine how my network processed. After immediately eliminating some, such as polynomial or linear regression, I decided to choose stochastic gradient descent because it only used one training example on every iteration, which made it extremely time efficient, but also allowed it to find the absolute maxima and minima, which made it very accuracy efficient as well. I combined this with my learning rate of 0.01. I found that too high of a learning rate would mean that the optimum point on the descent was missed, whereas too small would mean that the network was stuck in a valley. I then combined all of these features together with my stochastic gradient descent algorithm, 11-layer neural network, and my 0.01 learning rate to have a final training accuracy of approximately 94.3 and a testing or prediction accuracy of 98.13. I then moved on to my transmission system. In this, I wanted to create a device that could be able to communicate between the water pipes, which is where my device was located, and the water plant, thus facilitating that communication. I decided to use LoRa, or long-range radio technologies, in order to be able to do so, because they were able to transmit small amounts of information over long distances. I also created contamination codes, which reduced the amount of information that would need to be transferred between the LoRas. I would have a transmitting LoRa in the water pipes and a receiving LoRa in the water plant, and the contamination code, for example, would be 0. If 0 was transferred, that would indicate that this was clean water and no contamination was detected. In my end-to-end flow, I begin with the cron job, which uses the microscopic imaging system to constantly take pictures of the water sample. It sends it to the AI processing where a classification is created. From this classification, a contamination code is generated, which is then sent from the transmitting LoRa to the receiving LoRa, which will be able to notify authorities if any contamination is present, which will mean that we are able to reduce its spread greatly. This final device costs approximately $75, and I'm currently working with my local authorities to implement it in my community. In the end, I truly believe that with NARID, we can change the world. Simply one water droplet at a time.